In this lesson, we're going to review how to create a convolutional neural network and how to train and test it on the Cypher dataset. Then I'm going to show you how to do frequency ablation using PyTorch's fast Fourier transforms. The link to this Colab notebook will be in the description of this video. So in this first cell, we're simply importing the Cypher 10 data set, both the training data and the test data. We select a batch size of 64 and we create two data loaders, one for training and one for testing. And we print some of the characteristics of the data. We see that there are 50,000 training examples in this data set. There are 10,000 test examples. There are 10 classes into which we're trying to classify these images. Each batch, as we defined, has a size of 64 examples. And here we have channel height and width. There are 3 channels because it's a color image, and height and width are 32 for each image. In PyTorch, the channel number comes before rather than after the image size. Just for fun, we'll print 30 random images and their labels. This is what they look like. And now we get to creating our CNN. We have to do this on GPU. It would be too slow to do it on CPU. So you put in this line, and we define a CNN class. In order to be able to classify these color images on these backgrounds that have some complexity to them, we need a fairly large CNN. So this particular CNN has 3 convolutional blocks. You don't have to have these many convolutional layers in your final project because you'll be dealing with simpler images, but each of these convolutional blocks has 2 convolutional layers separated by 2 ReLU layers and finalized with a max pooling layer. They all have the same structure. So we start out with 3 channels corresponding to the 3 different color channels as our input to the first convolutional layer, and we come out with 64 channels. We submit that to a ReLU. Then we take our 64 channels from here and we keep the output at 64, and then another ReLU, and then we do a max pooling layer. So by the end of the first convolutional block, we have 64 channels, and because of our max pooling, we have halved our image size from 32 by 32 to 16 by 16. So this is the size of the output of the first convolutional block. By the end of the second convolutional block, we have further increased the number of channels to 128 and further reduced the image size. It's actually a feature map size. Each of the channels is considered a feature map. Has a size of 8 by 8. And by the end of the third block, we have 256 channels, each of which has a size of 4 by 4. Then we submit this to our feed forward network or fully connected layers. First, we have to flatten this. So we have a flattened layer, and then we submit the flattened output, which has a size of 256 times 4 times 4 is just a vector as the input of our first linear layer, and we reduce that to 512. We add a ReLU layer and a dropout layer. We'll come back to the dropout layer. Then we get the output of this, which has a size of 52, and submit it as the input of our second linear layer. And we further reduce its size to 256, another ReLU, another dropout, and finally we get the output of our second linear layer and give it to a third linear layer and reduce it to a size to an output of 10. We need an output of 10 because we have 10 classes in our data set into which we want to classify our images. The purpose of the dropout layer is regularization. Basically, dropout with a parameter of 0.5 will silence 50% of the neurons in the network and will combat overfitting. So now that we have our convolutional layers, which we have called self-features, and our fully connected layers, which we have called self-classifier, we can just write our forward image. We give the images X to the convolutional layers, and the output of that is a set of features which we have extracted from our images, and then we give those features to our feed-forward network, which we have called classifier, and the output of that is a class prediction. So this is our model. It's important to put our model on the GPU, so don't forget this line. We define a loss function. In this case, we'll pick cross-entropy loss. We define an optimizer. We'll use stochastic gradient descent. We give it a learning rate of 0.01. Here I've given it a momentum and a weight decay. For your final project, you can just use a lower learning rate of 0.001, and you don't need momentum and weight decay. Then we define a training function and a test function. In the training function, we set our model to training mode, and then we extract one batch at a time from our data loader. We put the images and the labels for each batch onto GPU, and then we submit each batch of images to our model, which we have defined previously, make a prediction, and then we compare that prediction against the gold label, and we apply the cross-entropy loss function to it to come up with a loss. Then we backpropagate that loss. The loss point backwards simply computes all of the loss gradients all the way to the beginning of the network. Then the optimizer step line applies those computed gradients to all of the weights and biases in order to update them. Finally, it's important to reset the optimizer to 0 so that it's ready for the next batch of inputs. And then we print our statistics in the process. The test function is sort of similar, except that here you put the model to evaluation mode, not to the training mode that we had before. Here it's important to say with torch no grad, because we do not want PyTorch to be computing gradients during testing. That's only done during training. Again, we extract our batches and we put them on the GPU. We make a prediction. We compared the prediction to the gold label and apply the cross-entropy loss, and we compute a loss, and we use that loss to calculate the accuracy of our predictions, which we return. So finally we run it. We choose 10 epochs, and we train our model during those epochs and print the test statistics at each epoch. And here's what we see. At the end of the first epoch, we have a test accuracy of 28%, but it keeps increasing with each epoch. By the end of 10 epochs, we have a test accuracy of 80%, which is pretty good. So 80% is the accuracy of our model on the test data set without any filtering of the test images. This all just shows us some of the 30 random pictures from the data set, from the test data set, and the predictions that our model has made. If the prediction is correct, it'll appear in green. If it's incorrect, it appears in red. And you can see we have a few reds consistent with our 80% prediction accuracy. Here we have classified an ostrich as a cat. Here we've classified an airplane as a bird. So now we have a trained model. It's time to do our frequency ablation. We don't train our model during this step anymore. We just use that trained model and we simply apply our frequency ablation to the test images for the purpose of evaluation. So first, as you remember, our magnitude spectrum or frequency spectrum is two-dimensional, and the points on that spectrum that are close to the center have a low frequency, and points that are distant to the center have a high frequency. So this function simply uses a torch mesh grid to compute a radius, which allows us to filter a particular frequency. Then we define our three filters, low pass, or three masks for our filters: low pass mask, high pass mask, and band stop mask. For a low pass mask, we give it a radius and a cutoff. So a radius is a particular location on the magnitude spectrum, a particular distance from the center, and if that distance is less than the cutoff that we have given the mask, then it'll pass that particular frequency through. It'll return true here. The high pass mask does the opposite. If the radius that we have given it is greater than the cutoff, it'll pass that radius, that particular frequency through. And the band stop mask, as I said before, is the opposite of a band pass mask. It will take two cutoffs, a low cutoff and a high cutoff, and it'll compare the frequency radius to these cutoffs. It'll pass only the frequencies that are lower than the lower cutoff and higher than the higher cutoff, but will suppress everything between the low and a high cutoff. So that's why it's a band stop mask. So now that we have our masks prepared, we are ready to do our Fourier transforms, and we'll use PyTorch's fast Fourier transforms. As we've discussed before, NumPy, SciPy, OpenCV, they all have their own Fourier transforms, but PyTorch's Fourier transforms have the advantage that they can run on a GPU and they can be applied in batches by simply defining or specifying the dimensions to which we want to apply them. So here we give it a batch of images, and we submit this batch of images to PyTorch's fast Fourier transform. We specify that we only want the transform to be done on dimensions 2 and 3. Remember, each batch has a certain number of images in the batch, certain number of channels, and then height and weight. We only want the Fourier transform to be applied to the height and weight dimensions, so we specify those dimensions. Then, just like we do with all the other Fourier transforms, you have to shift it. So we use FFT shift here, and then we filter it. So we get the shifted Fourier, and we simply multiply it by whatever mask we're handed in this function. It could be a low pass, high pass, or a band stop mask. We just multiply it by that. So now that we have our filtered and shifted Fourier transform, we simply do the inverse shift, and then take the inverse Fourier transform of that, and take the real component of that, and we end up with our filtered image, our image that has been frequency filtered to either pass the low frequencies or the high frequencies, or suppress a particular band of frequencies. So now we can evaluate our model with the mask. Again, we have already trained our model once. We don't want to retrain it. So we set our model to evaluate, and again with Torch without gradients, because we don't want to compute gradients in the evaluation modes. We get our images and labels, and we apply the masks to the images to filter the images. We make predictions on the filtered images, and then we see how many of those predictions are correct, and we return an accuracy. And this simply runs the frequency ablation sweeps at we have a max frequency, which is also known as our Nyquist frequency. That's the maximum allowable frequency for a two-dimensional image. And we divide that into 10 steps, ranging from 0.05 of the max frequency to 100% of the max frequency for the purpose of plotting. We trigger our low pass, high pass, and band stop filters. And this is what I was telling you in the previous lecture. Our band pass filter takes a low cutoff and a high cutoff. The high cutoff, we give it the cutoff frequency, and the low cutoff is just half of the cutoff frequency. And then we just plot it. The rest is just mechanical stuff. And here is the plot I showed you before for the frequency reliance curve for this particular data set. And again, I also did this with Butterworth filters. Here are the Butterworth filters. They're applied in the same way as the ideal filters, and again plotted, and we end up with very similar images. So next, I'll show you the skeleton code for your final project in the next video, and what you need to do to complete it.